So let's just prove it. First off, though, this whole thing really relied on the fact that if A divides B, A is less than or equal to B. Let's go ahead and prove a little lemma real quick. And so I'll say lemma. And lemma, remember, the nice little funny word, it's a little tiny thing. It's a little tiny math fact that we use to prove a bigger one. So that's a tiny fact we use to prove a theorem. So our lemma is going to be for all A in Z plus, and for all, formally this should have been a comma. There we go. For all B plus and for all B in Z plus. I'm actually going to use N and M. Just have to confuse X and Y. For all N in Z plus and M in Z plus, N divides M implies that N is less than or equal to M. Because once we prove that, it's gonna make our bigger theorem easier. So proof. So remember the way you start any of these direct, and we think this is true, by the way, from what we just did on our side. So remember the way you do any of these direct proofs is, there we go, is you start off, just let N and M be any arbitrary positive integers. And if you can prove it works for any arbitrary positive integers, well, heck, it's got to work for all of them. If it works for any positive integers, it must work for every positive integer. You know what I'm saying? So, proof. Let N and M be any arbitrary but particular positive integers. That's how we start all these guys. So then, positive integers, yeah. Now assume N divides M. Because this is how you prove conditionals. To prove conditionals, you assume the hypothesis and then show the conclusion must be true. Because it's all we care about. To prove a conditional, all you care about is that whenever the hypothesis is true, the conclusion is true. Because if the hypothesis is not true, we consider it vacuously true, and we're good. Ooh, what do we got here? But hey, if you want to write arbitrary slash particular slash part, totally fine with me. And in fact, in probably next week, I was gonna say like we're gonna abandon the arbitrary but particular thing. We're just gonna say let N and M be positive integers, but we're gonna assume it's there. So we're gonna get past assume. If you want to write arb slash part, but I say if you want to write arb slash part to mean arbitrary but particular, go ahead. Fine with me. So the point is to prove a conditional, you assume the hypothesis and you need to show the conclusion is true. So let's assume N divides M. In the case where N divides M, then by definition, there is an integer k equals M. It says my internet connection's unstable. Can you guys see me? Hopefully it's over. So the point is that we know that N equals MK, right? And then we can use our little trick we were talking about. We can say that notice let's see. Teleport a little bit. Okay, sorry about that. Hopefully I'll come back in a second. But anyway, notice since 1 is less than or equal to k, implies that m is less than or equal to k, or less than or equal to mk, both sides by m, since m is positive. If it were to have that, thus m doesn't equal to mk, which equals n by definition. So m is equal to n as desired. So the point is, right, if n divides m, n is going to equal m times k, and then k is going to be less than or equal to 1, or sorry, k is going to be greater than or equal to 1, meaning m is going to be less than or equal to m times k in particular, right, because k is bigger than 1, so if we multiply, it's going to be bigger. But mk equals n, so m is less than or equal to n. Now, I want you guys to do this every single class, all right? Put your lawyer caps on for a second. Put your lawyer caps on and say you're trying to prove me wrong, right? Say you're trying to find a hole in my argument. Where's kind of a giant hole in my argument right now?
Would it be in saying that k is positive but not justifying why?
Exactly, right? Like if you were if I was like the prosecution, right, and you were the defense, and then you go lawyer, you'd be like, objection, y is 1 less than equal to k. And remember, this is operating on, it's not leading. What's it called? There's a word for it when you're operating on assumptions that aren't proven, that aren't on evidence, right? Yeah, we haven't shown this to be true. I mean, if it was true, it'd be great. We get what we wanted, but how do we know this is true? So we have a little bit of work to do. What we got in chat? Yeah, I mean, this, is that what's called a course? It's called a conjecture? Maybe it is. I don't know. I should blow it up on the wall. But anyway, the point is, yeah, so how do we prove this? And Taylor, I like the fact that you said we haven't proven it because you know it's true because you talked about it, right? So how can we show this? Well, here's the thing, right? K is an integer, but how do we know it's a positive integer? That's the hard part. Notes. Here's the thing, notes. And actually, I need a little more room than this. So what we want to say is that we want to look at k, which equals n. Yeah. So note n and m are positive. Thus, m greater than 0 but in particular, m does not equal 0. Why is it important that m doesn't equal 0? Because then n equals mk implies that n over m equals k by dividing both sides by m. And we needed m not equals 0 to do that, because if m equals 0, then you're dividing by 0, which you can't do when all this breaks down. But because we know it's positive, we can divide by n. So that means that n over m equals k. And by the way, I am using this double implications arrow correctly, what that's saying is that, what I'm saying there is that n equals mk if and only if n over m equals k, which is true, right? For our particular n and m here, this is a true implication zero to make. It is true that maybe you have this, you have this, maybe you have this, you have that. So, so we have n over m equals k. Note, I'll say since n and m are positive, k, which equals n over m, is also positive. And that's just like a math fact, integer fact you're allowed to know, right? If you divide a positive by a negative, you get, or if you add a positive by positive, you get positive. Negative divided by negatives, negatives. Positive divided by negative, or sorry, negative divided by negative is positive, but negative divided by positive or positive divided by negative are all negative. But did you look that up as an opinion or conclusion formed on the basis of incomplete information? That's not very fun to yell in court, if that's what it's actually called. Objection. An opinion or conclusion formed on the basis of the point. Yeah. So k is positive. And why is that important? Well, because it's also an integer. K is a positive integer. K is a positive integer. Since k is a positive integer, 1 is less than equal to k by observation of z plus. Meaning there, just, we looked at z plus and saw that 1's the furthest one on the left, basically. 1's the smallest. Which we can do because these are still properties in the integers. We're allowed to know the integers work. And I say allowed, I'm just saying the integers are kind of like, I don't mean allowed as in it's like legally allowed. I mean allowed in terms of, that's just like the assumptions we're going to start with in this class. You could go a little deeper, but that wouldn't quite be intro to discrete math. That would be advanced discrete math, which we actually won't have here, which is a bummer. But anyway, yeah. So we have this right here. 1 is equal to k. Oh, and boom, then we have it, right? This is exactly what we need to do the rest of the proof. So if 1 less than equal to k, and it's going to do the rest quickly because we already have it, and that is that then 1 is less than or equal to k if and only if m is less than or equal to mk. By multiplying both sides by m, since m is positive. We keep the since m is positive bit just to say that's why we don't flip the inequality. Therefore, 1, therefore m is less than or equal to mk, which equals n. Done. Any questions in this lemma? I think it's a pretty simple lemma. It's just saying that if n divides m, oh, wait a minute. I did all this backwards. Sorry, let's just change this to m divides n implies n. You're going to assume that m divides n. And no one caught me on that. I think that would be the other way around. But anyway, yeah, hope that makes sense. or that implies, yeah, there we go. The point is, all we're saying that is that if one number divides another number, that's all we're saying. Any questions? So it's a kind of simple lemma, a little complicated to prove, right? Really, it wasn't complicated. There's some technicalities we had to deal with, right? Making sure we're dividing by things that aren't zero, making sure our inequality algebra works out, right? All that kind of stuff.